You might be surprised to learn that even with the equation v equals f lambda, speed equals frequency times wavelength, the speed actually doesn't depend on the frequency and it doesn't depend on the wavelength. It's important to keep that in mind when we do these equations, that they don't imply causality. It doesn't say that this speed depends on what this frequency is, and that this frequency, if we change it, that will cause an effect, or cause a change in speed here. Speed is actually determined by characteristics outside of both frequency and wavelength. So wave speed does depend on, well, two main factors here. So first off, speed depends on well, generally the type of wave that we're working with. Some types of waves just travel better or faster than other types. In particular, I'm thinking about light waves, or I guess a little more generally, electromagnetic waves. They travel very, very quickly. So you see lightning before you hear thunder. The lightning is traveling much, much faster. Sorry, the light is traveling much faster than the sound is in that case, because light waves travel faster than sound waves. Now, aside from that, the type of wave, the other thing that matters here is just generally the properties of the medium, material that the wave is going through. And so the properties that are going to be most important here are going to be the density of the material. The density of the material is important here, and then the temperature is important as well. Now, density is not an obvious characteristic that would influence the speed of a wave, but we need to keep in mind what waves are, how they travel. So for mechanical waves, that's the waves that have to have a medium, mechanical waves travel, they propagate because of interactions between atoms and molecules, between individual particles. So if I have a lot of particles that are really packed closely together, and say I push on one of them, that one motion is going to cause a larger effect on more particles than we get if we push just a single particle around over here. So maybe these are all, they're repelling each other by the electric force. So if I push this one over this way a little bit, it's going to tend to repel everything that it gets close to. So moving this over here is going to push this one over here, and it's going to push this one over that way, and this one over this way, and we get kind of this spreading of that effect. We get, well, a ripple moving outward from that point. And then if I move a single point here, I see that, well, that is a lot closer to these other dots, and so the force between those, since force is inversely proportional to distance, the force is going to be larger, and it's going to have a larger effect on more particles. You could also think of this in terms of collisions. If I'm having a wave that's transferring through because of collisions, then when I push on say this end, all of these particles on this end, they're going to collide more rapidly and more often with other particles because they're really crammed in there. So high density media have high speeds for waves, at least for mechanical waves. It turns out that for an electromagnetic wave, having a lot of particles in the way, that just slows things down. Electromagnetic waves, they travel best through empty space. So for electromagnetic waves, it'd be the opposite relationship. Low V for EM waves here. And here, be a high V for EM waves. So we'll come back to electromagnetic waves and talk more about those later on. For now, though, let's focus on the mechanical waves. So density was one thing that mattered here. Temperature matters as well. And so, again, we think of this probably easiest in terms of collisions. If I have, say, two particles and they're always in motion, remember the kinetic model of matter, They're always in motion, and the temperature tells us about how fast they're moving. So if I have really slow movements here, these are things that are pretty cold. And so if I say push on this end, push on this molecule, it's going to start to move over this way, but it moves pretty slowly. And eventually, you have some collision or some interaction that causes this one to move off this way. But it's a pretty slow process. Now, if we have really rapid movement of these particles and we push on this one and make it knock over in the other direction, then it very quickly gets over to the next particle and we have that interaction that way. So the speed of the particles, which we can learn about by looking at the temperature of that material, that influences the speed of the wave or the speed of the disturbance propagating through that material as well.